this set of notes, we're going to look at moment generating functions. But before we can talk about moment generating functions, we first need to define what are moments. So many random variables have the same mean and the same variance, and we would like to characterize that probability distribution of y even further. So we're going to start out with a definition here, which is the kth moment of a random variable taken about the origin. And so you'll notice here in the notation, we have mu, there is a prime in the superscript, and k in the subscript. So the prime in the superscript, that's what's going to let us know that this moment is taken about the origin. And you'll notice that it is equal to the expected value of yk. So if we look at a couple different moments, if we have the first one, notice that this is going to be equal to just the expected value of y to the first, which is just the expected value of y. So notice that the first moment of a random variable is just equal to its mean, which we've seen before. So that usual expected value that we've worked with, that is what we have here. If we look at the second moment about the origin, notice this is equal to the expected value of y squared. And we could keep on going. So the one that you're most familiar with is going to be that first one. We could also define the k moment taken about its mean, and we call this the kth central moment. And so notice the difference here notationally is we don't have the prime and the subscript. And then in the definition, notice that we're looking at the expected value of y minus its mean to the kth power. So we'll first look at the first central moment. So mu1 is going to be equal to the expected value of y minus mu to the first power. But notice that is equal to the expected value of y minus mu, which is equal to the expected value of y minus mu. But remember that the expected value of y is mu. So we have mu minus mu, so this one is just 0. So the first central moment is just 0. The second central moment you have seen before. So notice this is the expected value of y minus mu squared, which by definition is the variance. Now there's no reason that we have to stop at 2. You can take k up as high as you want. And so you may ask, well, why do we care about all these different moments when typically we only look at that first moment about the origin and that second central moment? And the reason for this is that it ends up that we can actually use these moments to help us define distributions. But before we do that, let's just look at an example and practice finding some different moments. So consider this distribution that we have right here. So let's first go through and just find the kth moment for this distribution. So we're going to start out, and I should say that is the kth moment about the origin. So let's just start here with the definition. Okay. And so next we're going to apply our definition of expected value. So remember that by the definition of expected value, we are looking at the integral from negative infinity to infinity, y to the k times f of y dy. Now, in this case, if we look at our distribution, y is only defined between 0 and 2, so we know that that integral is going to be equal to 0 anywhere else. So we can just focus on the integral from 0 to 2, y to the k, and then next I'm going to put in the actual f of y. Okay. To make this just a little bit easier on myself, next thing I'm going to do is just expand this out. I've still got the integral from 0 to 2. I'm going to multiply through that 1/2 y to the k. So first, if we have that 1/2 y to the k times 2, then that is just going to be y to the k. And then I'm going to have minus 1/2 y to the k plus 1. And again, dy. Okay. Then after we integrate, we have y to the k plus 1 divided by k plus 1 minus 1/2 times y to the k plus 2 divided by k plus 2. And we are going to evaluate that from 2 to 0. Right. And then from there, we have 2 to the k plus 1 divided by k plus 1 minus 1/2 times 2 to the k plus 2 divided by k plus 2. And this is then equal to 1 over k plus 1 times 2 to the k plus 1 minus 1 over k plus 2 times 2 to the k plus 1. So factoring out that 2 to the k plus 1, we have the following. Which is equal to 2 to the k plus 1 over k plus 2 minus k plus 1 over k plus 1 times k plus 2. And then simplifying, that is equal to 2 to the k plus 1 over k plus 1 times k plus 2. And so you may ask, well, why would we want to do this? Well, the reason that we can do this is now that we have what this is equal to, we can now find any of those moments about the origin that we want. So, for example, if we look at the first one is going to be when k is equal to 1. So we're going to have 2 to the 2 divided by 2 times 3, which is equal to 2/3. We could also find the second moment about the origin. 2 to the 3 times 4, which is equal to 2 divided by 3, and so on. So notice the initial work was a lot, but once we get through that initial work, I can find any of those moments about the origin that I want. And really, if we look at the work that was involved here, the work that involved here wasn't much more than just taking the expected value of y. So if we need several of those higher order moments, it's really useful to go through, find these moments generically in terms of k, and then we can find whatever moments it is that we want. And so that leads us to this idea of the moment generating function. So suppose that the expected value of x to the I is equal to the expected value of y to the I for all I, 1, 2, all the way up to infinity. So in other words, what that says is x and y have the same moments about the origin. Then under some fairly general conditions, it can be shown that x and y have identical probability distributions. So notice what this is saying. This isn't saying if x and y have the same mean. This is saying if x and y have all of the same moments about the origin. So it can't just be that they have the same mean and they have the same standard deviation. It has to be that all of their moments about the origin are the same. And if that is the case, then we can say that they have identical probability distributions. And so we can use what is called a moment generating function to find all of the moments for a random variable y. So one thing to note here is that the moment generating function is kind of like a fingerprint or DNA of a probability distribution. It uniquely identifies the probability distribution. And so since each moment since each distribution is going to have a unique moment generating function, then we can use the moment generating function to help us figure out which distribution a random variable has. And so here's the definition of the moment generating function. The moment generating function evaluated at t is equal to the expected value of e to the ty. And really, y is the random piece here, so that y should be capital. So the moment generating function for y exists if there exists some b greater than 0 such that the moment generating function evaluated at t is less than infinity for all absolute value of t less than or equal to b. In other words, what this is saying is it has to exist on an interval containing 0. Okay? And so let's look at some examples. So the first thing we're going to do is we are going to go ahead and find the moment generating function for the gamma distribution. So to start out here, we have m of t, and then by our definition is equal to the expected value of e to the ty. And then by definition of expected value, we have from 0 to infinity. And remember, this is for a gamma distribution. So for the gamma distribution, y is defined for 0 to infinity. So that's why I'm integrating from 0 to infinity here. We have e to the ty, 1 over beta alpha, gamma alpha, y to the alpha minus 1, e to the negative y divided by beta, dy. And so here we just have the distribution function for the gamma distribution. So it may be a good idea to pause here, go back, look at the notes where we define the gamma distribution, and just confirm that that is what we have for the gamma distribution. And I went and double checked for you. If you go and check that, that is going to be in module 4.3 is where that's located. All right. So next, just to make this easier on myself, I'm going to go ahead and pull out that constant. So we have 1 beta to the alpha, gamma alpha. Then we have our integral. And then I want to combine these two terms right here. So this term and this term. So I'm going to have e to the ty minus y over beta dy. All right. So the next thing I'm going to do is I'm going to work with the exponent. All right, so looking at that exponent, notice that I've got ty minus y beta minus, or probably that, now that equals, notice there's a y term shared here. So this is going to be equal to minus y times 1 divided by beta minus t. So I just rearranged my terms there. But notice that this is equal to minus y times 1 minus beta t divided by beta. And then this is equal to minus y divided by beta over 1 minus beta t. And you might say, well, why would you do that? Why did you arrange it this way? And you'll see here in just a moment why we do that. So I'm going to rewrite my moment generating function. And so now, looking at this integral looks really nasty. And I think to myself, man, I really don't want to have to do that. So what I'm going to show you all is a trick that is commonly used when it comes to statistics or biostatistics and looking at integration. So we're going to use the fact that we know that if I integrated over the entire PDF, that would have to integrate to 1. Okay? So recall here, let me change my color here. So recall that if x was distributed as a gamma distribution, then f of x looks like the following. Okay. So ignore that leading constant for just a moment. Let's look at this piece of that gamma distribution. Notice we've got y to the alpha minus 1. Well, here I've got a y to the alpha minus 1. And then I've got an e to the negative y divided by some beta. And notice here I've got e to the negative y divided by something. So notice that this looks very similar to a gamma distribution. Really, the only pieces we're missing are the leading constant, and we notice the beta term is slightly different. So what we can do to help us with our integration is we can multiply by this constant, and then we'll also need to multiply by 1 divided by this constant so that they cancel each other out, and we'll end up with something that integrates to 1. And so again, this is a very common trick so that we don't have to actually do the integration. So what I'm going to now have is I'm going to say, well, this is equal to, I have my original constant, and then I know that in order to make this thing look like a gamma, I'm going to want to multiply by something similar to this. So I'm going to leave myself just a little bit of space. I'm going to rewrite, now there's my integral. I'm going to leave myself a little bit of space. I've got y alpha minus 1 e to the negative y divided by beta divided by 1 minus beta t. Okay, so if this whole term is my new beta, I can see what I'm going to need out front is a 1 divided by my new beta that whole thing to the alpha, and then my alpha between these two gammas is the same, so I'm still going to have gamma alpha. Now, in order to make this true, since I multiply by 1 over this term here, I also have to multiply by this term. So in other words, that way I'm really just multiplying this entire thing by 1. So by doing this, the reason this is so nice, and there's a dy here, is because this whole piece right here, I'm now integrating over the sample space of a gamma distribution. So we know that if we integrate over the sample space of any of our distributions, that this whole piece has to be equal to 1 as long as beta over 1 minus beta t, we do need that to be strictly greater than 0. And so to solve here to see what this implies about t, you could find that this is the same as t being less than 1 divided by beta. And so you would do that by, you'd have to solve for this inequality. In terms of t. So now we only have this first piece to look at. So notice here we have 1 over beta alpha, gamma alpha, times beta to the alpha, 1 minus beta t to the alpha, gamma alpha, but notice that this term and this term cancel, this term and this term cancel, and so we end up with this is equal to 1 minus beta t to the minus alpha, where t is less than 1 over beta. And so this gives us the moment generating function of a gamma distribution. Actually, we'll just, to save space, let's put m of t equals here. All right, so again, that's the moment generating function of the gamma distribution. So to check this, we could put in t equals to 1. So notice that m of 1 is equal to 1 minus beta to the minus alpha. So here we have that first moment, but you might say, but wait a minute, I thought this was supposed to give me that first moment about the origin, which we know that for the gamma distribution is alpha beta. Well, next we have how to use the moment generating function. So if the moment generating function exists, then for any positive integer, m to the k evaluated at 0. So here we've got, this is defined as, so notice the k is up here in the superscript, that this is equal to the kth derivative at m of t. That is what's actually going to give you that first moment. All right, so coming back up here. So let's use our moment generating function the correct way and see what we get. So here we have 1 minus beta t to the negative alpha. So the first thing we're going to do is take the kth derivative, or probably the first derivative. So if we look at that first derivative, this is going to be equal to minus alpha to the 1 minus beta t minus alpha minus 1 times negative beta. And then you can show that this is equal to alpha beta 1 minus beta t minus alpha minus 1. And then we're going to evaluate at t is equal to 0. And so if we evaluate this at t is equal to 0, you should find that that first derivative evaluated at 0 is equal to alpha beta. So we do have to be careful here. The moment generating function helps us to generate those moments, but we can't just evaluate it. We do have to take the derivative to find those moments. So let's look at another example. We're first going to start out by finding the moment generating function of the Poisson distribution, and then we will then use the moment generating function to help us find the moments of the Poisson distribution. All right, so starting out, we're just going to have our definition of the moment generating function. So notice here I'm not integrating because the Poisson was a discrete random variable. So I have the definition of the expected value for a discrete random variable. Remember that for a Poisson distribution, y goes anywhere from 0 all the way up to infinity. Okay. Notice that this is equal to the sum, y equals 0 to infinity, e to the t lambda to the y over y factorial e to the negative lambda. Now, directly evaluating this sum would be really, really nasty. I don't want to do that. So we're going to use a very similar trick to what we did with the gamma distribution. So remember with the gamma distribution, I had this integral, and I said, this integral looks really nasty. I don't want to integrate it. Is there a way that I can use the fact that if I integrate over the sample space of a PDF, it integrates to 1 to simplify that expression and get rid of the integral? We can do this exact same thing here with this summation. The summation looks really nasty. I don't want to do this, but I know that if I sum over the sample space of a PMF, then that sum is going to be equal to 1. And so this looks very similar to a Poisson distribution. And in fact, it looks like a Poisson that has parameter e to the t lambda. So using that fact, I'm going to do again something very similar to what I did before. So I'm going to rewrite this moment generating function. I'm going to start with this piece that I have here. The sum from y is equal to 0 to infinity e to the t lambda y over y factorial. Next, notice that the e to the negative lambda, it doesn't depend on y, so I can actually bring it outside the sum. So I'm going to bring it outside. And so now I would like this to look like a Poisson so that I know that that piece will sum to 1. Well, to do that, I could place an e to the negative e t lambda here. So in other words, I'm using this as that new parameter for a Poisson distribution. But if I'm going to do that out here, I have to multiply by e to the et lambda, so that I'm really just multiplying the entire expression by 1. And if I do this, again, notice that this piece right here, this is the PMF of a Poisson distribution with parameter e to the t lambda. So this entire thing is going to sum to 1, leaving me just with e to the negative lambda, e to the et lambda, which is equal to e to the lambda, e to the t minus 1. And so this is our moment generating function for a Poisson distribution. So let's use this to find both mu and sigma squared. So again, we've got that the moment generating function is equal to e to the lambda, e to the t minus 1. So we're going to take the first derivative. And remember here we're using those superscripts to tell us what derivative. So let's first recall that d dx e to the x is equal to e to the x. So if we're going to take the derivative here, notice that the first thing we're going to have is e to the lambda, e to the t minus 1, and then multiply that by d dt lambda e to the t minus 1, which is equal to e to the lambda, e to the t minus 1, lambda e to the t. Okay. So now we're going to substitute in 0 for t. Remember, we do this because that's how we're going to find what mu is equal to. So notice this is equal to e to the lambda times e to the 0 minus 1. times lambda e to the 0, which is just equal to e to the lambda times 0, which is also 0, so that piece is 1, times lambda times 1, which is equal to lambda. And so we can see here that we get lambda, and we know that lambda is the mean of a Poisson distribution. So next, to find sigma, you're going to take the second derivative. Okay, so in other words, m2t. So this one I'm going to let you check on your own. But remember, we've already taken the first derivative, so here you're just going to take the derivative of e to the lambda e to the t minus 1 times lambda e to the t. And you should find that when you do that, you get e to the lambda e to the t minus 1 times lambda e to the t plus lambda e to the t times e to the lambda e to the t minus 1 times lambda e to the t. And notice there's no need to simplify here, because remember that to get that second moment about the origin, we want to evaluate that second derivative at 0. So once you evaluate that second derivative at 0, you should find lambda plus lambda squared. And you might say, well, wait a minute, that's not what the variance of a Poisson distribution equals to. And you're right. But remember that this is the second moment about the origin. In other words, this is equal to the expected value of y squared. To find sigma, or to find the sigma squared, to find the variance, we need to remember that sigma squared is equal to the expected value of y squared minus the expected value of y squared. So here we're going to have lambda plus lambda squared minus lambda squared, because we just found the expected value of y up above. And notice this is equal to lambda. So we do get that the variance of the Poisson distribution is equal to lambda. So in the next set of notes, we're going to continue looking more at the moment generating function, and we're going to see how we can use it to determine the distribution of a function of random variables.